So recall from the previous example that the invariant factor decomposition of the sixth group is the direct product of the integers modulo 60 with the integers modulo 12. Now for the seventh group, in the first row we have 4, 9, and 5. In the second row we have 2, 1, and 1. And in the third row we have 2, 1, and 1. So the first invariant factor is 4 times 9 times 5, which is 180. Second invariant factor is 2, and the third invariant factor is 2. And so the invariant factor decomposition of the seventh group is the direct product of the integers modulo 180 times the integers modulo 2 times the integers modulo 2. Now for the eighth group, in the first row we have 4, 3, 5. In the second row we have 2, 3, 1. And in the third row we have 2, 1, 1. So the first invariant factor is 4 times 3 times 5, which is 60. The second invariant factor is 2 times 3, which is 6. And the third invariant factor is 2. And so the invariant factor decomposition of the eighth group is the direct product of the integers modulo 60 times the integers modulo 6 times the integers modulo 2. For the ninth group, we have 2, 9, 5 in the first row, 2, 1, 1 in the second row, 2, 1, 1 in the third row, and 2, 1, 1 in the fourth row. So the first invariant factor is 2 times 9 times 5, which is 90. The second invariant factor is 2. The third invariant factor is 2. And the fourth invariant factor is 2. So the invariant factor decomposition of the ninth group is the direct product of the integers modulo 90 times the integers modulo 2 times the integers modulo 2 times the integers modulo 2. And finally, for the 10th group, in the first row we have 2, 3, 5. In the second row we have 2, 3, 1. In the third row we have 2, 1, 1. And in the fourth row we have 2, 1, 1. So the first invariant factor is 2 times 3 times 5, which is 30. The second invariant factor is 2 times 3, which is 6. The third invariant factor is 2, and the fourth invariant factor is 2. And so the invariant factor decomposition of the 10th group is the direct product of the integers modulo 30 times the integers modulo 6 times the integers modulo 2 times the integers modulo 2. So as an exercise, find all abelian groups of order 792 up to isomorphism and determine the invariant factor decomposition of each group. And as a second exercise, let P be a prime and let alpha be a positive integer. Prove that the integers modulo p to the power of alpha is indecomposable. Okay, so new definition. A transformation of a set X is a bijection, which we'll call phi, mapping the set X back into itself, if in addition the set X is finite, that is, the cardinality of the set X is n for some positive integer n, then the bijection phi, mapping X back into itself, is called a permutation of the set X. So a permutation is a transformation of a finite set, and we can think of this as a reordering of the elements in the set. So next we'll prove a lemma. Let X be a set, and let sigma and tau be transformations of the set X. Then the composition of sigma and tau is a transformation of the set X. So proof. Since sigma, which is a map from the set X back into the set X, and tau, which is a map from the set X back into the set X, are both bijections, the composition of sigma and tau, which is a map from the set X into the set X, is also a bijection. And hence the composition of sigma and tau is a transformation of the set X. So next, we'll prove another lemma. Function composition is associative so proof. Let F be a map from the set A into the set B. Let G be a map from the set B into the set C. And let H be a map from the set C into the set D. Then the composition H of the composition G of F is a map from the range of the composition of G of F, which is A, into the set D and is defined by h of g of f of the element A is h of the value of the composition of g of f at A, which is h of g of f of A. Similarly, the composition of h of g with f is a map from the domain of f, which is A, into the range of the composition h of g, which is D, and is defined by h of g of f of the element A is h of g of the element f of A, which is h of g of f of A, and hence h of the composition g of f of the element A is the same as the composition h of g of f of A for every element in the set A. Okay, so new definition. The function, which we denote I sub x, mapping the set x back into itself, defined by I sub x of the element x is the element x, is called the identity function on the set x. Now clearly, the identity function is a bijection, and so it is the unique transformation that maps each element of a set back onto itself So new definition. Let f be a function from the set A into the set B. Then the function g, mapping the set B into the set A, is the inverse function of the function f, if and only if the composition g of f is the identity function on the set A, and the composition f of g is the identity function on the set B. So next we'll prove a theorem. Let f be a map from the set A into the set B. Then the function f has an inverse if and only if the function f is a bijection So proof. Suppose that the function f, mapping a into b, has an inverse, which we denote f inverse, mapping b into a, so let x and y be two elements in the set A, and suppose that f of x is equal to f of y. Then f inverse of f of x is equal to f inverse of f of y. Now f inverse of f of x is the composition f inverse of f at x, and this is equal to the composition f inverse of f at y. This is the identity function on the set A, taking as an argument x on the left-hand side, equal to the identity function on the set A, taking as an argument the element y on the right-hand side, so we have x is equal to y. Hence the function f is injective. So now let b be an element in the set B. Then b is the value of the identity function on the set B, taking as an argument the element b. And this is the composition f of f inverse at b, which is f of the value f inverse of b, where f inverse of b is an element in the set A. And so for every element b in the set B, there exists an element a in the set A, such that b is equal to f of a. And hence the function f is surjective, and thus the function f is bijective. So conversely, suppose that the function f, mapping a into b, is a bijection. Then define the function g, mapping b into a, by g of b is the element a, if and only if f of a is the element b. Notice that we can define the function g this way because the function f is a bijection. Then the composition g of f is a map from the set A into the set A, where g of f of the element A is g of the element f of a, where f of a is b, so this is g of b, and g of b is the element a, and hence the composition g of f is the identity function on the set A. Similarly, the composition f of g is a map from the set B into the set B, where f of g of b is f of the element g of b, where g of b is a, and so this is f of a, and f of a is the element b, and hence the composition f of g is the identity function on the set B, and thus the function g is the inverse of f. So as a third exercise, let x be a set, and let T of x be the set of all transformations of the set X. Prove that the set of all transformations of the set X is a group under function composition. Okay, so we'll end here for today. Next time we'll continue to look at transformation and permutation groups. So I hope you have enjoyed the 21st lecture. Thanks for watching.